Tonight I'm going to talk to you all about Imhotep, which is our system at Indeed for analyzing large amounts of data and also doing machine learning. So I'm Jeff Plaisance, as Andrew said. I'm the engineering manager for the search quality team, and I help people get jobs. And Indeed is a search engine for jobs. We go out on the web, find all the jobs that are available, pull them into one place so that job seekers can come to one place and find a job. If you go search for a job on Indeed, this is what you're going to see. So here's results for a person who wasn't sure what query they wanted to do, so they don't know what kind of job they want. They just know they want a job in Austin, Texas. So this is our search page, and we're continuously experimenting with changes to this page. But to do that, we need data so that we can be sure that all of the decisions that we make are improving the experience of the job seeker when they use our site. Indeed is a data-driven organization. We try to make sure that there's data to back up all of the decisions we're making as much as possible. So data-driven organizations need great tools in order to deal with the data they need to make these decisions. You need to be able to ask the right questions of your tools, and you need to be able to interact with and explore your data sets. So Imhotep is our primary tool for doing that, and Imhotep allows us to build decision trees, as Andrew talked about last month, for those of you who are here, and analytics. It also runs most of our analytics systems. So at Indeed, we have a philosophy about how analytics should be done. So analytics systems should be interactive. You should be able to do your query on the system and get an answer within seconds, a minute, or at most. Very, very quick, so that once you see that result, if you think, oh, maybe I want a little bit different question, you can change it and then run it again and iterate on the question that you're asking until you're asking the right question. And if you have to put in your queries a day in advance and then wait for data to get collected and then go back and look at the results, you're not going to be able to quickly find out what you need to know to make the right decisions. So we also believe that analytics systems should not downsample. When you start downsampling your data sets, you can still get the same answers at a high level, but you lose the ability to drill into your data sets and really find the anomalies and the outliers in your data. So as soon as you start downsampling, you can't do that anymore, which it's not good. It's important to find the outliers and fix them, or account for them, whatever the case may be. And also, analytics systems should not approximate things. So the issue with approximations is that they introduce assumptions. So if I have an operation that I can do that's an approximation, and I, as the programmer, know what the assumptions that that approximation is making, when I go and do that query, I can take that into account subconsciously and account for it. But if someone goes into that system and runs that same query and doesn't maybe know how it's implemented and know what the assumptions are, they might get a result that is a bad result. But they won't know it because of the approximations that you've done. So if there's some kind of leaky abstraction in your approximation, you can get serious errors in your results. So Imhotep is a system that we like to think of as a system that answers questions. And one question you might ask Imhotep is, what was the weekly average query time in the last quarter from people doing the query software? So Imhotep can answer that question. It can also answer the question, what percent of job search results pages are for page 2 and beyond? So how many of our job seekers didn't get the results they wanted on page 1 or wanted more results? And it can also answer questions like, what are the top 5 most common queries in each country? But the first question we're going to look at is, what was the number of job searches from March 9th to March 23rd? But before we can even answer that question, we have to kind of define what we're counting as a job search here. So we're going back to our search engine's result page here, our job search page. And we've got a query and a location. So in analytics, we think of this page here as being a document. It's something that you're searching and that you can do analytics with. So this search is an event. This event has properties. One of the properties of this search event, is that it had a query that was done by a user. It has a location. It has a set of 10 impressions. So this is an impression. One of these results is what we call an impression. It has some other properties, like whether or not the user clicked on the impressions or not. So there's a lot of different things we can have in this search event document. So that's kind of where the Imhotep system starts, is at the document level. So this is a document in our job search index. We've got a query, a location, a number of impressions, clicks, and the time that it occurred. And maybe some other fields that I'm not showing here, but then we're going to zoom out one layer here. So the highlighted part is our document. And what we're seeing here is one layer zoomed out. It's what we call a shard. It's like a piece of the bigger picture, but it's a set of documents. And it's important to note here that these documents have an identifier, which we call a doc ID. And it's an integer. It starts at 0, and they're consecutive. That's going to be important later. So then we're going to zoom out one more level here to the server level. The server in Imhotep consists of a set of shards. So here's our server. We've got 6 shards in this server. And as you can see, each shard corresponds to a time range. So Imhotep is a time-sharded system. We take our events that we get in, we split it up into time ranges, and the documents from a time range always go to the same shard. Going out one more level, we have the whole cluster. So several machines, each having several shards, each shard having several documents. And if you want to interact with this system, this is the layer at which you do it. The client here creates a session talking to all the machines. So if you're accessing the system, you're going to be accessing all of the machines in the system in parallel. So also of note is that the session is like, it's a stateful thing. So if I want to start talking to Imhotep, I'm going to open the session, I'm going to do some operations, and then I'm going to close it later. So let's go back to this example here. How many job searches do we have between March 9th and March 23rd? This is actually a really easy question to answer, given what I've told you so far. All we have to do is find the shards of our job search index that correspond to that time range and count the number of documents in each. I'm not actually going to tell you what the answer is, but that's how you would do it. Now let's ask a slightly different question. How many job searches did we have per day in that time range? And there's going to be a little bit different way of doing that. It's going to require explaining a few more concepts here. The first of which is metrics. So a metric in Imhotep is a number. It's defined to be a 64-bit integer, and a metric has exactly one value per document. Within the Imhotep system, we have random access to these metrics by doc ID, which is one reason why it's important that doc IDs start at 0 and are consecutive. We use an array for that, so that's how they have random access. So some examples of metrics. Time is a metric. There's one time value per document in our job search index, the time at which the event occurred. Clicks is a metric. How many clicks happened? Impressions is a metric. How many jobs do we show? Revenue is another metric. It's a very important metric. Anything that's a number and has a single value, exactly one value per document, is a metric. The next concept is groups. Each document is placed in a group within the context of a session. So the groups have a number. When you open your session, every document starts in group 1. They can move to other groups throughout the course of the session, with group 0 being a special group that refers to documents that have been filtered out. So those are removed to docs that you don't care about in your session anymore. So the groups are stateful. They're scoped to a session. When you create your session, we initialize the group state. You can manipulate it during your session, and when you close your session, we throw that state away. And you do these operations called regroup operations in order to move the docs between different groups. So let me tell you one type of regroup operation that we could use for this query about how many job searches happen per day. We call this one metric regroup. So the way a metric regroup works is we take a metric, we iterate over the values for that metric, and we take that value and we take a start value. In this case, the start value would be the start time of our query. We subtract the start value from our metric value. So the metric value is the time at which the search occurred. We can divide by the bucket width. So the bucket width here would be 1 day. So convert it all to the same time unit, so seconds. Do the division, and it'll give you a group number. And so the server will do all this with just 3 parameters, start, end, and bucket width. And this is really useful for making graphs, for defining your x-axis for a graph. It does this bucketing feature, which is really nice for time series graphs. Lastly, there's a get group stats command, which for each of our groups is going to sum a metric for all of the docs that are in that group. So for our example, we're going to regroup on the time metric, and then we're going to get group stats on the count metric. So we want to know for each of our groups, each group corresponding to a particular day, how many of our documents fall into that group. Count is always 1 for every doc, no matter what. So that'll answer this question: how many job searches happen per day in this time range? Our next question is a little more complicated. It's how many job searches happened per day between this time range in the US? So Imhotep can also answer this question. It's going to require going a little bit further into inverted indexes, because inverted indexes allow us to very efficiently do this operation. So to go further, I'm going to have to explain how an inverted index works. So an inverted index is like the index in the back of a book. The words in the book index equate to what we call terms in an inverted index, and the page numbers in the book index equate to what we call the docs in the inverted index. So we're going to have a list of terms, and for each term we're going to have a list of docs, and our term list is sorted. That's important because we need to be able to binary search our term list to be able to find the term that we're looking for the query. And our doc list is also sorted, and you'll see why in a second. So let's first talk about how an inverted index is sort of constructed. So we start with a standard index, which is just a list of documents. So we have 5 documents here, 4 fields. The fields are query, country, impressions, and clicks. And we have values for each of these fields in each of these documents. The first thing we're going to do is we're going to find all the unique terms in each of these fields and sort of explode this view so that we know which term occurs in which document. So here's what that looks like. So we can see that software in the query field occurs in document 0 and also document 3, and so on. So the next step in constructing an inverted index, and this is the actual inversion here, is we're going to flip the rows with the columns. So right now, we've got the fields across the top, and down we've got doc IDs, and we're just going to flip that around. And this is what that looks like. So now we've got our query, our fields, and then our terms for that field. And then for each of those terms, we have some docs. And the last step here is just going to be compressing that set of docs into a sorted list of docs, like so. So now we have a list of docs for each of these terms. And inverted index allow you to quickly find all the documents containing a term. And you can kind of build on that to find all the documents containing one term, and then find all the documents containing another term, and then do more complicated operations to intersect those term lists to perform complex Boolean queries. So any kind of Boolean query you can implement easily on top of an inverted index. And if you need an inverted index implementation for some problem you have, you should use Lucene. It's open source, it's fast, it's widely used, and it's well tested. So back to our question. How do we find out which of these searches were in the US? We use our inverted index. So the first thing we're going to do is go to the term US in the field country. We're going to zoom in on that here. And then that gives us a doc list. So the operation that we perform on Imhotep in order to do this is what we call query regroup. is our second type of regroup we're talking about. And what a query regroup does is it regroups all the docs which do not match a Boolean query to group 0. So in this case, our query is a one-term Boolean query, which is, does this document contain the term country US? So one term. If you remember, group 0 is the filtered out group. It's a special group. So that's going to filter all of those docs that don't match this query out of our data set so we can count the remainder, and that'll give us our count per day. The next type of regroup is what we call a term regroup. I want to talk about this one real quick. So a term regroup will split your documents that are currently in a group into one of two new groups. And it does it based on the presence or absence of a particular term. So we could also use this term regroup for our country US query. So in this example, if we have the term country US in the document, it goes from group 1 to group 2. If we don't have the term country US, it goes to group 3. And if we just counted group 2, we could perform the same operation here. But we actually use query regroup in practice for this. The next is a generalization of term regroup that we call a multi-term regroup. So a multi-term regroup, you give it n terms instead of just one, and we're going to get n plus 1 new groups out of that. So as you can see, we've got country US, country Canada, and country France is our 3 terms. And then in our 4th group, everything else. So if it contains country US, it goes in 2, and so on. And this is another very useful type of regroup. So this query, we're answering it with a query regroup. So our inverted index here started off as that standard index I showed you, which is just a set of documents. That's for our organic impressions data set. For the last 5 months, that's 102 terabytes of data. That's pretty big. You wouldn't really want to put that in RAM on one machine. That's expensive. So the inversion itself is a form of compression. It's sort of like dictionary compression, because you're taking your terms and only storing one instance of it, and then just storing a number for each instance of it. So the inversion itself actually cuts the size of the data set in half, from 102 terabytes to 51 terabytes. That's still really big. So in practice, for inverted indexes, you need to do a lot of optimizations to make them fast. And the primary type of optimizations in inverted indexes is compression. And the reason that you need to compress your inverted indexes is because compression gives you a few things. It lets you fit more of your index in RAM. So the more of your index that you have in RAM, even if it's compressed, the faster you can access it, given that your compressor is fast enough. It also counterintuitively makes better use of your memory bandwidth. So if I have a compressed data set on disk, I can load more information into RAM when I copy those bytes than if it was uncompressed on disk. So if I compress it on disk, load it into RAM, and then decompress it, I get higher information throughput, not data throughput. The data throughput's the same, but the amount of input of information that I'm moving is greater with compression. So this comes at the trade-off of higher CPU usage and time to decompress. So in practice, inverted index compression algorithms are extremely well optimized. And this is a very active area of research. So the most common inverted index compression method is called delta and variable length integer encoding, or Varint encoding. So the way that works is you have your doc list. So as I said earlier, your doc list is sorted. You can replace your doc list, so it was a sorted list. You can also represent that as the difference between each doc and the doc before it. So each doc and the previous doc. So that's the delta between the docs. You can restore your full doc list from that information. So the deltas are going to be very small numbers in comparison to the original doc IDs. They're going to be small numbers. And the key to this is that if we use less bits to store the small numbers, with the trade-off of using more bits to store the larger numbers, we will save space overall. So delta encoding. So if this is our doc list for the field query term nursing, that's what the delta encoded version of that doc list looks like. It's just Just the differences between the adjacent terms. That's all we have to store. And we can restore the original doc list from that information. So there's a few different methods of small integer compression that are commonly used in inverted indexes. You need to use this in combination with delta encoding for it to have any benefit. So the one we use is called Varint encoding. So I'm going to explain that now. Let's say we want to Varint encode the number 9,838. The first step is we're going to look at what that number is in binary. So this is the representation of that number as a 4-byte binary number. In Varint encoding, what we do first is we take the least significant 7 bits of our number. If you look at this number, you can see that there's no useful information in the top 2 bytes. It's just all zeros. In the low 2 bytes, you can see that there's a lot of information. There's 14 bits of information. So in Varint encoding, the first thing we're going to do is we're going to take the least significant 7 bits and write them in the low 7 bits of our first output byte. We then have the question of what is the top bit of our output byte? What is the 8th bit of our output byte? So we need to look at the remainder of the number to determine that. And the way we do this in Varint encoding is if there are 1s, if there's remaining information in the rest of the bits, we're going to store a 1 in this top bit to signify that another byte follows this one. Otherwise, we put a 0. So here we can see that we do have 1s. We have remaining information to code. So we're going to put a 1 in our output. We then take our next least significant 7 bits and write them to the low 7 bits of our next byte. And again, we look at the remainder of the bits. They're all zeros, so we don't have any more information to encode. So we signify that by putting a 0 in the top bit here. So as you can see, this is our Varint encoding of 9,838. It's only 2 bytes instead of 4, so we saved 50% space. So back to our organic data set example, with the original data set, it was 102 terabytes. The inversion brought it down to 51. And the delta Varint encoding is going to bring that down to 17. So that's a very big savings. So we've cut the original data set down by a factor of 6. So we can buy 6 times less RAM if we want to keep this whole data set in RAM. And then for whatever amount of RAM we do have, we can fit more of it in RAM so we can access more of our data set faster. We actually have our own inverted index format that we use in Imhotep. It's called Flamdex. So in Flamdex, we have 2 files per field. We have a terms file and a docs file. This is useful because we can add fields to our index without rebuilding the entire index. So if we have a derived field or something, we can add it later and not have to rebuild the whole thing. Whereas in Lucene, all the fields are in the same file. So to add a field, you have to rebuild the whole index. Flamdex has its own Varint decoder implementation that is very fast. It's faster than what's currently available in Lucene. And the other thing about Flamdex is that we've omitted term frequencies and positions. So this is a feature that you normally want in an inverted index that you're using to serve search queries. But for analytics, for Imhotep, we don't need them. So we don't have them because we don't want to waste time with them. We don't want to waste time decoding them or anything. So we just drop that feature. So Varints. Varints are nice because we get good compression. We can fit more of our index in RAM, and we get higher information throughput for the information we're reading from disk, and also into higher levels of the cache, higher levels of the memory hierarchy. The downside is that this encoding I've told you about, you have to decode 1 byte at a time. This requires 1 branch per byte, and it's a highly unpredictable branch. So there's a lot of branch mispredictions. Branch mispredictions are one of the slowest things you can do on a modern processor. So Varints are generally not all that fast to decode. We have our own Varint decoder that is a little bit better. So what it's going to do is it's going to decode 12 bytes at a time. And I'm going to tell you how it does that. Here's our 12 bytes. The first thing we're going to do is we're going to look at the top bit of each of these bytes. We're going to use an Intel instruction called pMoveMaskB to extract the top bit out of each of these bytes. into a number, into a 12-bit number. And as 2 to the 12th is 4096, we're going to take this number that we got out of the top bits of these bytes and look it up in a 4096 entry lookup table. This lookup table is going to tell us a lot of things about this number. It's going to tell us how many ints we're going to decode out of this number. It's going to tell us the sizes and offsets of the varints. It's going to tell us the length of the longest varint that we're decoding. And it's going to tell us how many bytes of this input we're going to consume. So let's look at this number in detail. As you can see, the first bit is a 0. That means the first integer in this list is a 1-byte integer. Then we have a 10, which marks a 2-byte integer. It's our second int. Our third int is a 1 byte. Then we have another 2 byte, another 2 byte, we have a 1 byte, and lastly we have this. We can't decode this on this particular pass because we don't have a 0. It's just 3 ones. That's not a full int. So here we had 6 whole ints. The longest one was 2 bytes. We can decode 9 of these bytes in this pass. Then on the next pass we'll catch whatever this next thing is. So we have decoding options for up to 12 1-byte varints at a time in parallel, 6 1 to 2-byte varints, 4 1 to 3-byte varints, or 2 1 to 5-byte varints. We can do all that. So in this case, we're going to decode 6 1 to 2-byte varints in parallel. And the first step of this is that we're going to pad our 1-byte varints out to be 2-byte varints so that we're only dealing with 2-byte ints. Fortunately, there's an Intel instruction that makes that really easy. It's in the SSS E3 instruction set. It's one of my favorite instruction sets. It's called pshuffb. It lets you shuffle the bytes around in a register. So that's what we're going to do. We're going to decode 6 varints from 9 bytes here. We've got 3 1-byte varints. We're going to pad them out to 2 bytes. So pshuffb does that for us. We just pass it the right operand, and that happens. So that's another thing we looked up in our lookup table. It was the operand to pshuffb. So the next step here is that we actually have the least significant bytes first. That's not going to work. We need them second. So we're going to reverse the bytes here. So I'm just going to do that. The third step is that we need to mask out the ones. We don't care about our connecting bits anymore. We know that we're only dealing with 2-byte numbers. And so we don't need these 1s and 0s anymore in the middle. So we're just going to mask them out. It's an AND instruction. Lastly, we need to shift the top bytes over by 1 bit. So that's just going to be a mask, a shift, and an OR. And so we do that. And now we've encoded, or we've decoded, 6 integers in around 10 instructions without any branches. And it's less than 2 instructions per variant. So this is going to be a lot faster than doing it 1 byte at a time. This is really important for us because Imhotep spends around 40% of its CPU time decoding variants. This is the bottleneck in Imhotep. This vectorized decoder is around 3 to 5 times faster than the one we pulled out of Lucene originally. And it can decompress around 1.5 gigabytes of data per second. So switching from the original decoder to this decoder gave us around double the overall system performance. All right, so the next thing we're going to talk about is a different type of query. So this is what we call a top terms query. And what we're asking here is what are our top 5 locations that people search for jobs in? That's what they are. But let me tell you how we're going to actually figure that out. If we had this thing called term stats, which is, let's take a field, and for that field, we're going to go through every term in that field and get some stat, the sum of some stat, in this case count, for that term, the number of docs that contain that term. We could answer this query. So we get our term stats, we find the top 5 by count, and then that's our answer. So we're going to have this concept of a term stats iterator, which for each term in a field, we're going to sum a metric across all the docs containing that term. But then we have the issue of having to compute this across a set of machines. It's not just one machine. We're going to take advantage of the fact that we have these sorted inverted indexes with these terms already sorted in them. So from each of these machines, we're going to be able to generate a sorted term stats iterator, sorted on the term. So here we have 3 sorted term stats iterators, sort of from the bottom up. And we're going to read the first element of each. So from the first one, we're going to see that we have Atlanta with a count of 16. From the second, we're going to see we also have Atlanta, count of 12. And the third, we have Atlanta with a count of 21. Now we're going to compare them all. We see that they're all the same. So we're going to sum the counts, and we're going to output that into our merged term stats iterator. Now we're going to look at the next element of each of these streams, advance the pointers. So now we have Austin, Austin, and Austin again. So here, again, we have the same term from all the iterators, so we're just going to sum and then advance again. So next up, we have Boston, Chicago, Boston again. So here, we can see that Boston is only in 2 of the iterators. And to keep our output iterator sorted, we need to make sure that we're outputting the lower of the terms that we have available now. So we have 2 terms available, Boston and Chicago. Boston comes first lexicographically, so we're going to output Boston on this iteration. And then we're going to advance only the 2 iterators that contain Boston. So now we have Chicago, same thing. And then Dallas is our last term. So yeah, and that's our merged iterator, and then we can find our answer by streaming through it and finding the maximum. So here we have 6 of these term stats iterators that we're going to be merging. You can imagine that this algorithm generalizes to any number of term stats iterators that we're merging. But you can imagine also that if we scaled this to like 1 million iterators, it's going to get pretty slow. It doesn't scale infinitely here. So one approach we could take in order to scale this up is to layer our merge. So if we can merge 6 iterators quickly, then we can merge 6 iterators on each of 3 systems. And then each of those will output another merged iterator. We can then stack that and have another merger, merging from those 3 streams, to get a total merger, merging everything. So this merger here, though, is probably going to be a bottleneck. We have this last step that's completely sequential. Everything here has to go through that step in order to be accessed by the client. So whenever we have a sequential bottleneck in a parallel system, the first thing to consider is Amdahl's law, which tells us that the maximum speed up we can get through parallelization of our system is dictated by the time needed for the sequential step. In Imhotep, the sequential part of this term stats iterator is going to be the last step in the merge. So if we can distribute that work better, more than we've done so far, we can get better parallelism. We can get a better throughput overall. So the way we actually do that is through this, what we call hash partitioning and then interleaving. So for our original iterators, we're going to take each of the terms out of that iterator and compute a hash. Say we have 8 merging threads. Our hash is going to be from 0 to 7, and based on that number, that term will go to that thread. So the same term is always going to go to the same thread. So that thread is going to get all the stats for that term. And then after we've done that, we can take our 8 output iterators and interleave them. We don't actually have any merging work left to do because we've already done all the merging there is to do. We're just interleaving. So here, in our original merge implementation, we expect that the final merger is going to be receiving in streams, and each of those streams is going to contain the same t terms. So it's going to require like n times t work to do that final merge step. So n times t. And then in our hash partitioning scheme, the streams received by the interleaver are going to contain disjoint sets of terms. And if we have in merge threads in our interleaving scheme, in our hash scheme, each of those merge threads is going to output t over in terms. And our final interleaver, we're going to be getting in of those streams. And you can see how in times t over in, the ins cancel. And we're only doing t work. So previously we were doing in times t work. And in this hash partitioning with interleaving process, we're only doing t work. So it's faster. It's got a lower complexity. Here's going to be an example of how that works. First, we're going to hash our terms. Green is going to represent terms that hash to 0. They're going to go to one merge thread. Orange is going to represent terms that hash to 1. They're going to go to the other merge thread. Now, we're going to zoom in on our green merge thread. So this is going to change a lot in a second. So there we go. This is what our green merge thread is receiving from each of those original streams. Now we're going to do the same merge procedure we did earlier. So we're going to look at the heads of each of these streams. We're going to see that they all contain the same term, and we're going to sum them. We're going to repeat this process. Merge the term Boston. Merge the term Dallas, just like we did before, except now we've got 3 terms. They're all merged. And then we're going to do the same thing for the orange terms. And then we're going to, at our interleaver, we're going to get these 2 disjoint sets of terms coming in. So we only have 5 inputs here, whereas before we had more. So the cardinality here has been reduced to just the number of unique terms that we have in our overall system. And then we're just going to interleave them. So we look at the heads of each stream, take whichever one's lower, in this case Atlanta, output it first. Austin is next. Then we've got Boston, Chicago, finally Dallas. So that's our interleaving scheme for that. It's faster than our previous merging. So our next topic is going to be shard distribution. So we have this problem of we've got all these shards of these data sets. And we have data sets for different types of events as well. So we might have one for people doing searches on our job search product. Maybe we'll have another data set for people doing searches on our resume search product. So those are each a distinct data set. And each data set is split into 1 shard per hour or day or some time range. And in our system, each of these shards has 2 replicas for fault tolerance. So we can lose 1 machine in our system, and we've lost no data. It's all still accessible. You can still do queries and everything. So we have this problem of how do we assign these shards to the machines that we have available. The considerations we want to look at when we're designing our shard distribution algorithm are going to be space. We want to make sure that we're using the same amount of space in every machine. We're not filling up one machine before another. We want to make sure that we're sending the same amount of query load to each of our machines. So that'll balance the CPU time. And a very important consideration here is that this system is very susceptible to stragglers. So that if you don't balance properly for query load, you're going to get into situations where you have one machine that's doing a whole lot of work, and when you're merging these sorted streams, you can only merge as fast as your slowest producer. So if you have this one really, really slow producer of this stream, it's going to slow the whole system down. So we really don't want unbalanced query load. We also really don't want hotspots. And lastly, we need to be able to add and remove machines to the system in a way that we can rebalance our shards to still meet all of our other balance criteria. So the first thing we have to decide when we're setting up this system and how we're going to run it is whether we can handle heterogeneous hardware. So we're going to have to decide if or how we're going to handle it. And I'm going to assert that you cannot balance for both space and load on heterogeneous hardware. And the reason why, okay, so say you have a 3 terabyte machine and a 1 terabyte machine. And you've got some shards. So let's fill each of these to 50% capacity. see what happens. So we've got 12 shards on the big machine, 4 shards on the little machine. They're both 50% full. If I'm a client of this system and I want to query 5 shards, I don't get to pick which shards I'm querying. I can't say I'm going to query 2 on this machine and 3 on this other machine. My question requires that I want to ask the system requires me to query a very specific 5 shards. They may only be on that big machine, and it's very likely that we're going to get an unbalanced distribution here. So what that's going to do is it's going to cause read hotspots on the big machines. We're going to be reading more data from those. We're going to increase the query load on those big machines. The other way we could do this balancing is just put the same number of shards on each of these machines. And this will work for a while until we fill up our small machines with data. Once they're full, we're going to have to start dumping all of the data onto the big machines, which is again going to cause these read hotspots. So either we have read hotspots or we have a ton of wasted space. So in practice, we just use a homogeneous system. Hotspots, when we're accessing any subset of a data set, so for example, our job search data set, you might want to query it for this month, you might want to query it for last month, you might want to query it for like 2 years ago. We want to make sure any of these subsets, when you query it, is going to spread the load as evenly as possible across the available CPUs, drives, and network. It's a hard problem to solve. But the first thing we're going to look at is whether we can just kind of randomly do this balancing and see if that's going to be good enough for our purposes. So if we randomly distribute our data across our system and then just like pick a machine that that data is on and read from it, we're going to be reading around 10% more data from our most loaded machine than from our least loaded machine. That's reasonable, but earlier I said we had 2 replicas of each shard. We can take advantage of that in order to balance better. If, when we're establishing our client session, we have a set of shards we want to talk to. For each of those shards, for the first shard we want to talk to, we say, based on the context of what we're doing in our session, which machine that shard is on are we currently reading less data from right now? And we're going to pick that machine. So whenever, at each choice for which machine you want to read a shard from, you're going to greedily choose the one that you've picked the least times so far. And that's going to improve our balance. And it's actually going to make a big difference in our balance. And here, we get around 1% more data from the most loaded machine than the least. And this is definitely good enough for what we need to do. That's a really good level of balance. And the way we actually distribute the shards onto these machines is not truly random. It's deterministically random. It's using this method called rendezvous hashing. The way that works is that we're determining the assignment of a shard to a machine, and we're determining it based solely on the list of machines that exist. So if you know the list of machines that exist, and you know what shard you have that you want to put on one of those machines, you can compute a deterministic function to discover that. And the way it works is we're going to hash all the pairs of that shard's identifier with each of the machines, the identifiers for each of the machines. And each of those is going to result in a number. We're going to say a number from 0 to 1. And for those numbers, we're going to pick the largest hash value. And the machine that hash value could correspond to is where we're going to put that shard. So I'm going to show you some examples. If we have this shard with this name, we can hash the concatenation of that shard name with the name for machine 1. And that gives us a number. We can do it again for machine 2, get another number, and so on for all of our 5 machines in the system. And we can see that the largest one is M5, and then M3, then M4, and so on. So if we map those hash values onto our number line here, going from 0 to 1, we can say if we want one replica of this shard, we're going to put it on M5 because that's the largest hash. Now this really generalizes well to multiple replicas. Because if you want 2 replicas, you put the second one on M3, and so on. If you wanted 3, you put it on M4. Rendezvous hashing is really nice for this because it doesn't require any coordination between the machines. They only need to know that machine list in order to determine where that shard should go. So it's a deterministic algorithm, and The really great thing about it is it doesn't require any centralized storage for our shard-to-machine assignment. So that really simplifies the system for distributing these shards around. Let me show you another example. This is going to be an example where we're adding a machine to our system. Because earlier I said that when we add machines, we want to maintain our balance and we want to move the smallest amount of data possible. So here we have 6 shards, each represented by one of these vertical bars. And we have 2 machines, the blue machine and the red machine. We're going to add a third machine. It's going to be the green machine. And for each of these shards, you can see we have 2 hashes right now. And whichever one is higher on this number line is where the machine that shard is currently on. So for each of these shards, we're going to add a new hash for our new machine. So we're going to pick the hash, calculate the hash. For the first shard, it was here. It's not the largest number. And this is with only one replica of each shard, by the way. So for this shard, the hash is not the highest, so we're not going to put that shard on this machine. For the second shard, it is the highest. So here we're going to move this shard from the red machine to the green machine. Compute this for the third shard. It's not the highest, so we don't move it. Again, for the fourth shard, we don't move it. It's not the highest. Fifth, it's not the highest, we don't move it. For the last one, it's the highest, so we're going to move this shard from the blue machine to the green machine. And now we've gone from having 6 shards, 3 on each of our 2 machines, to 6 shards with 2 of each on each of our 3 machines. So the math behind that tells us that it's actually going to rebalance in the way we want is that the expected maximum hash for any given shard is given by machines over machines plus 1. In our example, we had 2 machines. So the expected maximum hash for each shard is 2/3. That's the expected value of the maximum hash on that machine. Now, for our new machine, we're going to pick a number uniformly distributed random between 0 and 1. And we're going to move that shard to that machine if that number that we've picked, based on our hash, is greater than our previous max. So our previous max was 2/3. So we have to have a number higher than 2/3, and the probability of that occurring is 1/3. So it's 1 plus the number of machines over 1 over machines plus 1. So probability that each shard is going to move to the new machine is 1/3. We had 6 shards. The expected value with a probability of 1/3 is going to be the expected value is going to be that we're going to be moving 2 of those shards to the new machine. So as I told you earlier, Imhotep answers questions. And this was one of the questions I said that it could answer. And I'm going to tell you how we can answer this question with the primitive operations that I've described so far. So what was the weekly average query time in the last quarter from people doing the query software? This is how you can do that on Imhotep. We're going to do our query regroup command on the term query software to filter our data set to only the documents where the user did the query software. Next, we're going to do our metric regroup command with the width of 7 days to get into our 1 week buckets that we wanted. And lastly, we're going to do our get group stats command on the query time metric in order to get the total query time for each of these weeks. We're going to also do our get group stats command on the count metric in order to get the number of queries. And we're just going to divide, and that gives us an average. So that's going to answer our question. Turns out this is a really common operation that people want to do, and we built a tool for it. It's called Ramses. So you can put in queries, and it will do this bucketing operation for you. So this is actually the answer to that question, computed by Ramses. Our average time per SERP for the query software in the last quarter was around 150 milliseconds. Our next question. What percent of job search result pages are for page 2 and beyond? We can calculate that too. First, we're going to get the group stats on count the total number of documents in our job search index, the number of searches users did. We're going to do a query regroup, and this is a little more complicated Boolean query than I've shown so far, but this is for all the documents that are not on page 1. So it's a negated query. So it's minus page 1 So this gives us all the documents that were on page 2 and beyond. We're going to get group stats again on count. So this is going to give us the number of searches that were for beyond page 1, and then we're just going to divide. And that's going to give us a percentage. Ramses can do that too. So as you can see, 42% of our queries were for page 1, and 58% of our queries were for page 2 and beyond. Our next question was a little more complicated. What are the 5 most common queries in each country? The way we're going to calculate that one is we're going to use that multi-term regroup command that I described briefly earlier. We're going to do that on all the distinct values of the country field. So we're going to get 1 group per country. And then we're going to take our term stats iterator that I described, and it's actually extended a little bit from that. So it doesn't just give us stats for a single term. It gives us stats for the individual stats for every group within that term. So given a term, for each group which has documents that contain that term, we're going to sum the stats for those documents that contain the term and give you a group stat. So we're going to do that for the query count. And that, for each of our countries, that can give us the number of times that that query was searched in each of those countries. From there, we can calculate the maximum count for each country, for each group, and that's our answer. So we have another tool that can do that really easily. So you don't actually have to write code to do multi-term regroups and TGS iterations and so on. It's called IQL, which is, as you might have guessed, Imhotep Query Language. It's kind of like SQL. The major distinction here is that our things in our select clause are not rows, and they're not columns, as in SQL. They're actually sums of metrics. So in this case, we're going to be summing the count metric from the job search data set in this time range. And we're going to do these couple of regroups. The first regroup is on country, as I said. And then this last group by is actually implemented through this term group stats operator. And this query will give us our answer to our question that we had. And IQL is pretty powerful. Pretty much every other tool that we've developed that does analytics at Indeed, all the web app tools, can use IQL, can do those queries that they do in a single IQL query. It's very powerful. Imhotep is our large-scale analytics system. It's what we use for almost all of our data processing, all of our analytics, all of our decision making. We also use it for machine learning. If you were at Andrew's talk last month, you heard how. So what Imhotep gives us that's really a big deal is it gives us a set of primitive operations that allow us to implement the same set of data analysis operations done on like a relational database, but it allows us to do it in a distributed system at very large scale on large amounts of data. And in that implementation, we have a lot of other interesting things that we've done. So this Varint decoding thing is a pretty big deal. We have this very highly optimized stream merging algorithm. And we have this shard distribution using rendezvous hashing. And hopefully some of this stuff will come in use to some of you. And we're also very proud to announce that in the coming future, in the coming months, we're going to be open sourcing Imhotep. So all of you will be able to use Imhotep for your data sets that I'm sure are fascinating. I didn't mean that in a derogatory way at all. Like, seriously. I'm sure you all have fascinating data that you need to analyze using a tool like this. So you can use Imhotep in the future once we've finished with our open sourcing process. It's going to take us a few months. We need you to be able to build it in your system. Like currently, it's you need our build system even to build it. So what you need to know in order to be able to use this is you need to know how to get your data into Imhotep. So you'll be able to get your data into Imhotep through 2 methods once it's out. So we have what we call the TSV uploader, which you can just take a TSV, upload it into your system, into the system, and Imhotep will digest that and make an index shard. You can also build your shards in Hadoop directly with the Flamdex Hadoop builder. So also, you need to know how to access your data. So you can use the primitive operations that I've talked about tonight, or you can just use IQL. The primitives allow you to do a little bit more than IQL will allow you to do. I mean, you can't build decision trees with IQL. But for most analytics type things, IQL is pretty useful. So I'm really excited to see what types of analytics tools people can build using IQL on top of the system. All right, so the next talk we're going to be doing is going to be next month. It's going to be large-scale interactive analytics with Imhotep. So we're going to be talking about how we use Imhotep to analyze our data and all our tools that we have for doing so. It's going to be given by Tom Bergman and Zach Kokos, and it's going to be April 30th.